we learned that if you have a quantum system, you use a state vector or state function to describe the state of the quantum system. But there's an alternative. Instead of describing the state of a quantum system by a state vector, you can also define this quantity, which is the outer product between two state vectors, and form what is known as the density operator. Once you know the density operator, or density matrix, you know the state of the quantum system. And then say if you want to find the expectation value of an operator under the state of the quantum system, then you do this, you multiply A by the density operator and take the trace of this. And the trace of this can be taken by finding the matrix representation of A hat and rho hat. If you find a matrix representation, this product will look something like this, and you can find the trace quite easily. And trace is not dependent on the order. Okay, it's not dependent on the order. Because of this, then you can show also that if you have a density operator, you can find the equation of motion. So these are the equations of motion of the density operator once you know the Hamiltonian of the system. If you know the Hamiltonian of the quantum system, then you can find that this is how rho hat could evolve. Alternatively, you can write this as a matrix representation instead of operator representation. And then we use this to study two-level systems. To study two-level systems, there are many two-level systems in this world. One of which is just a, say you have a molecular system with many energy levels. You might just want to focus on the physics of two levels when these two levels are very close together, and you shine in light to see what happens to the behavior of this two-level system. You can approximate the Hamiltonian of this very complicated system by just a two-level system involving two eigenvalues and eigenstates. Okay, when the light comes in, you can assume that the light perturbs the Hamiltonian, so you add an additional term. This additional term has off-diagonal elements. What it means is that if there's no off-diagonal elements, the original Hamiltonian will only have stationary states. Those energy levels will stay either at E1 and E2 and not change. But under the perturbation of light, you have this additional perturbation Hamiltonian that causes a transition from level 1 to level 2. Okay? So this could be an atomic system, like laser interaction or light interaction with atoms. Okay. Another way that you find this kind of system is in MRI, magnetic resonance imaging, or NMR. Okay. Nuclear magnetic resonance. Okay, in that kind of system, what you have is that you have spins. And you have a bunch of spins, and if there's a DC magnetic field, B0, pointing in this direction, then the spins will split into two energy levels. If they are degenerate in the original state without a biasing magnetic field, then when you bias the spins with magnetic field, then the spin whose spin is aligned with the magnetic field will tend to have a lower energy state. And if the spin is disaligned or oppositely aligned with the magnetic field, then the energy state will be higher. So this might be lower energy state, and this might be higher energy state. And similarly, you might have things like this in atomic system. And then when you perturb this with the RF field, RF electromagnetic field, then you can cause the transition of the spin from one state to another one, or flip the spins, and that can be regarded as a two-level system as well. Okay? And where do you find spins? Where do you find spins in this world? You can find plenty of them in water. If you have water, you put them into liquid form, then they will dissociate into OH minus plus H plus. Okay, you have this dissociation. Water is H2O. So this is essentially a proton, and you have plenty of proton in fluid. So these protons move around in the human body quite naturally. And if you put a human body under the biasing of a static magnetic field, the proton spin will be split into two energy levels. And you can do magnetic resonance imaging with this kind of system. So we have plenty of protons in our body. And you can manipulate the spin so that you can make images where you can get the spins to go from this state to that state, and when the spin has a transition that release the energy, it gives out radio frequency electromagnetic field. Okay, you take the RF electromagnetic field to excite the state from one low energy state to the other one. And this is how MRI imaging is done with lots of spins in the human body. And the equations of motion that we have derived for this two-level system can also be applied to MRI if you wish to. But what they did was that we went through this work over here and derived the equations of motion. Okay, we actually worked this out in great detail. Rho hat, H hat minus H hat, rho hat. And now I will not distinguish matrix operators from quantum operators. So H hat would be just this quantity over here. Rho hat would be something which we call rho 11, rho 12, rho 21, rho 22. And you can derive this from a two-state quantum system quite easily. If a quantum system consists of two states, you can say that it has this kind of eigenstates, psi 1 and psi 2. And then if you were to form the outer product, okay, it can be replaced with the matrix representation A1 squared, A1, A2 conjugate, A2, A1 conjugate, A2 magnitude squared. And this is your rho 11 and rho 12. Okay? And then we see how that system evolved. We went through the algebra and found that the time evolution equations are of this form. The rho 21 dt is of the form of I h bar, rho 11 minus rho 22, E mu d plus E2 minus E1 rho 21. This is what we found for the time evolution equation rho 21. And then we can call this to be a kind of a frequency, because this is just the energy level between these two levels, and then you will have a corresponding frequency, and we can write that as being equal to minus I omega 21, okay, divided by h bar. And if you divide by h bar, or multiply this by h bar, we get this minus I omega 21. Actually, there should be a minus sign over here. Sorry, there should be a minus sign over here. Okay? And then we can call this delta rho. Delta rho is the difference between the probability of finding the electrons in energy level 1 minus the probability of finding the electron in energy level 2. So we can write this equation as being equal to minus I omega 21 rho 21, which is this term over here, plus a term that comes from the presence of the electric field, mu dE over h bar delta rho. Okay, if you look at this equation, what does it mean? Rho 21 and rho 1, 2 are the conjugate of each other. Rho 2, 1 is this quantity over here. Okay. What it says is that if the two states are correlated, coherent with respect to each other, if these two energy states are coherent with respect to each other, then their amplitudes, when you multiply to each other, will have a fixed phase relationship between them. Okay? And this phase relationship makes this quantity non-zero. You can take ensemble average of all the atoms that you have in the experiment that you are doing. This term will not ensemble average to 0, and this term averages to something like rho 2, 1. And rho 2, 1 would naturally, even if there's no exciting electric field, this term E comes from the exciting electric field. This is the electric field. Okay, and these two are there because of the presence of a light or an electric field from the outside, and mu d is the dipole moment of the atom. Okay, so if there's no electric field exciting the system, you will just have this system over here. Okay, if you have that system over there, then rho 2, 1 is something that behaves like e to the minus I omega 2, 1 t times a constant. So rho 2, 1 is something if E is equal to 0. If there's no exciting field, that's how this behaves. What it says is that there is an interference between these two energy states. Okay? They are correlated with an exact phase. And the correlation does not average to 0, and they have a very fixed phase relationship between them. And that phase relationship is given by omega 2, 1, where omega 2, 1 H bar is E2 minus E1. Okay, that is the interference frequency between the two energy levels. However, if you have an electric field present there, okay, the electric field will change the evolution of this correlation function between those two states. And that excitation is proportional to the difference in density or probability of the two energy level, or the atom or the electron being in the two energy levels. And then it's proportional to the dipole moment times the electric field. Okay? And if you look at rho 1, 1, how rho 1, 1 evolved, you can plug that in and derive that rho 1, 1, the equation of motion for rho 1, 1 is equal to minus I over H bar E mu d rho 1, 2 minus rho 2, 1. And then you find that rho 2, 2 is almost the same, okay, except for some sign change. I over H bar E mu d rho 2, 1 minus rho 1, 2. Okay? These are the diagonal terms of the matrix element of the density matrix. What it says is that if there's a correlation between the two energy levels, which is rho 1, 2, and rho 2, 1 at this quantity, if they are not 0, which means that they're correlated, then the presence of an electric field will cause this probability to change. Okay? And this is a probability of finding the electron in state 2. This is a probability of finding the electron in state 1. And the presence of the electric field, plus the fact that the correlation between them not been 0, will cause that probability to change with time. That's the meaning of these two equations. And we can combine these two equations into one by adding the two or subtracting the two. This would just give rise to the difference in the probability of the two states, and we can call it delta rho. Okay, delta rho is rho 1, 1 minus rho 2, 2. And then if you subtract these two, you get this equation. Okay, rho 1, 1 minus rho 2, 1. And you use the fact that rho 1, 2 and rho 2, 1 are related to each other. Okay, rho 1, 2 is rho 2, 1 complex conjugate. You can see it from here. rho 1, 2 and rho 2, 1 is just a complex conjugate of each other. Okay? And when you subtract these two equations, you get a new equation that would just be the difference between the two. But these two being the complex conjugate of each other, you can consolidate this equation and write this as being equal to E mu to D rho 2, 1 minus rho 2, 1 complex conjugate. So it's just equal to minus 4 over H bar E mu D times the imaginary part of rho 2, 1. Okay, so these are the two equations of motion that are important to us. And let's see how we can solve them. Okay. And these actually are the equations of motion for one atom alone so far. However, we can also write this as the equation of motion for an ensemble of atoms. We can imagine that there are many, many atoms. All of them are identical to each other. And then we shine in light to excite this atom. But this atom would be in motion and it would be in a thermal bath. Okay? So, even if there's no exciting electric field, even if there's no exciting electric field, there will be something happening to this system. Okay? One of the things that happens is that even if there's no exciting electric field, this equation of motion is not truly correct. Okay? What happens is that the thermal agitation between the atoms in the thermal bath will cause the system to lose correlation between the two energy levels. Okay? There will be some transition going from energy level 2 to 1 or 1 to 2 due to the fact that it's coupled to a thermal bath. So we will have to modify this equation, assuming that there's a thermal bath around. And so if there's a thermal bath, we change this equation by adding an additional term. Being equal to minus I omega 2, 1 rho 2, 1 plus I mu d over h bar e delta rho, okay, plus a term that is due to the thermal agitation. And you can look at the meaning of the last term. The meaning of the last term is that if there's no exciting electric field, if this had been 0, then the equation of motion would just be this one, minus I omega 2, 1 minus 1 over T2 rho 2, 1. What is the solution to this equation? It says that rho 2, 1 must be something of this form. T minus T over capital T2. Okay? If there's no excitation by external electric field. This is just a phenomenon to describe the fact that this correlation for this ensemble of atoms cannot forever be there. It will be lost due to thermal agitation, due to collision with other molecules and atoms. Okay, it will lose the correlation between the two states. And this will ensemble average to 0 after a certain time. And that time scale is T2. Okay, you will lose coherence. The energy states will lose coherence and this will ensemble to average after a while. And that is a phenomenological way to describe this phenomenon. Okay, so we just add this equation in that manner. And similarly, this equation has to be changed also. This equation says that if there's no electric field present, then delta rho is a constant. Delta rho will not change. Delta rho is rho 1, 1 minus rho 2, 2, which is the difference between these two probability functions, these two probability values. But if the system is under the agitation of a thermal bath, some of the energy level would jump between the two, even if there's no exciting electric field. Okay, we have to describe and incorporate those physics or physical phenomena into this equation, and how we do that is that we say that the delta rho dt would have to be equal to 2I over h bar E mu d, the original term that we had there. Okay, the original thing that we had over there, which is coming from here. Okay, plus the term that describes the fact that we are in a thermal bath. And what it says is that if E is equal to 0, and there's no excitation from the outside, you can say that delta rho is equal to, you can actually work this out, is actually constant times e to the minus t over t1 plus delta rho naught. Okay, I think this would be the solution to this equation. That after a certain time, delta rho becomes delta rho naught. This is the quiescent value of the population difference. If you think of this in representing the population difference between the two levels, if you have an example of atom, rho 11 minus rho 22 would just be the population difference between the two states. If you have many, many atoms that you are observing, okay, what this says is that if there's no exciting electric field, delta rho would reach this quiescent value. So there's a population difference even when there's no electric field exciting the system. And what is causing the system to have some population difference is the thermal bath, the energy from the heat around the system. That's what it's saying. Okay? So we modify this equation in this manner. Okay? Everybody sees this? That this is the homogeneous solution, this is a particular solution. If I set this to 0, and this is the thing and how it behaves. Okay?
Is there a minus in front of the 2I over h bar or not?
Let me see, I don't have a minus sign.
Because there is a minus there.
There's a minus there. Yeah, I don't have a minus. I shouldn't have a minus. Okay, sorry about that. I shouldn't have a minus. Then we take the imaginary part, the minus, and minus give you this minus. Okay, sorry about that. And so we have this thing, and then now we try to elucidate the physics more, to see what actually happens to this two-level system when we have a time harmonic electric field exciting this system. Let's assume that the electric field that we have is the sinusoidal electric field of this form, and that it is represented by two oscillating terms of this form. Okay, that is the electric field we have in this system. Now let's see how we can solve this equation when this electric field is present. How can we solve the two equations of motion? Equation 1 that we have here, and then equation 2. How do we solve these two systems? Okay. We will have to make some approximations known as the rotating wave approximation in optics. Okay. We can think of this as being two phases rotating in opposite directions. Okay, this in the counterclockwise direction, this in rotating in a clockwise direction. Okay, so you can imagine that if we have an electric field exciting the system, let's look at say let's look at this equation first. Okay, if E is of that form, okay, and then rho 2,1 has this typical form. This is a resonance form or the homogeneous solution for rho 2,1. Okay, had there not been any exciting field, okay, rho 2,1 would behave something like that. Okay, and let's assume that the damping term is very small. So if we assume that the damping term is very small, rho 2,1 is predominantly something that behaves like that. Okay, but then you're exciting the system with two waveforms. You're driving the system with two sinusoidal functions or two time harmonic functions. This term that comes in here has two driving terms. Okay? If this driving term, if one of the frequencies, say if this one, if omega is close to omega 2,1, then it will drive the resonance solution. This is known as the resonance solution of this equation over here. Okay, because the resonance solution should be very, very big. Okay? And then this other term will be off resonance because it's not hitting the resonant frequency of the system. You can think of the system as having a pole. The pole is close to omega 2,1. If you drive the system with two frequencies, this one, if it's close to the resonant frequency, will predominantly be the driving term. This one would drive something, some response for the system, but the response is small because it did not hit the resonance. Okay? So one of the conclusions that we can make is that rho 2,1 will respond with two frequencies, as you learn in your undergraduate course. When you drive a system with the time harmonic signal, the response are those that follow the two frequencies. Okay? But one of these will be very big, and the other one will be very small, because this one is closer to the resonance solution. Let's assume that omega is approximate in the vicinity of this resonance solution. So we can say that C1 is going to be much, much larger than C2. So this solution is approximately equal to that. Okay, if we are working around the resonance solution of the two. The problem, okay, this is going to be predominantly what happened. So rho 2,1 can then be approximately written as C1 e to the minus I omega t. Okay, ignoring the second term, even though there is some driving energy at that term over there. Okay, this is called the rotating wave approximation. And this is going to be slowly varying a function of time. Okay, this is going to be fast. Okay? So the C1 is the function of time, but slowly varying. So we can actually define this to be rho 2 or beta 2,1. Okay, we define this to be beta 2,1 and say that rho 2,1 is approximately equal to beta 2,1 e to the minus I omega t, where this is slow. Okay, the other one being fast. And if we make this approximation, then we can say that rho 2,1 is going to be something like that, and rho 1,2, which is the complex conjugation of rho 2,1, is going to be approximately equal to beta 2,1 complex conjugate e to the plus I omega t. Okay, rho 1,2 is going to behave like that. And now that if you substitute that back in, okay, substitute that back into this equation that we had over here, okay, substitute that back into this equation, and then you will have something like Okay, you will have something that you pick up as you substitute this back in, because this one has two terms over there. When you multiply these two terms out, it has two terms of a different frequency. But when you multiply this out with that, okay, you're only going to pick up the slowly varying term. You're only going to pick up the slowly varying term. You get four terms. If I substitute rho 2,1 with this and then rho 1,2 with this in here, okay, I'm going to have two exponential terms, and this has two exponential terms. I multiply them up, I have four exponential terms. Okay, of this four exponential terms, there's only going to be one that is slowly varying. The others have oscillations. Okay, I'm only going to keep the slowly varying term and ignore the other rapidly varying terms. So I'm going to rewrite this equation, keeping only the slowly varying term, and then ignoring the other term. And if I only keep the slowly varying term, I'm going to have this. Okay, this is the final equation where rho 2,1 has been approximated with this, and these are the slowly varying terms that I have. Okay, E has been replaced with E0 because when I substitute that in there, I get this E0 over 2. I have this term and multiply things out. I have four terms altogether, and then my four terms altogether, it will only pick out two slowly varying terms, I suppose. And the two slowly varying terms are these two terms. You want me to go through the detail of this? It's quite obvious. Multiply this together, get four terms, pick up the slowly varying terms, you get only two terms. The others are rapidly varying. Okay, the other are rapidly varying. And we are not interested in the rapidly varying solution because if you try to excite something with the rapidly varying term, okay, the response is going to be small. The response to the excitation is going to be small. And so we are only looking at the slowly varying response to the excitation. And if you do that, then we can also rewrite this equation too in terms of beta 2,1. Okay, so if I use the fact that the rho 2,1 dt, okay, rho 2,1 is related to beta 2,1 in this manner. Okay, if I use the fact that this can be written as the time derivative of the slowly varying term, okay, e to the minus I omega t minus I omega beta 2,1 e to the minus I omega t. Okay, if I make use of this fact, okay, and substitute back here to this equation, then I get a new equation of motion for beta 2,1 alone. Okay, that would be delta omega beta 2,1, because there is an omega coming from here. Okay, and then this delta omega is just equal to omega minus omega 2,1. Okay, because I have an omega coming from here, I have an omega 2,1 coming from here, and they don't really cancel. Let me call that difference delta omega. At resonance, that term will cancel each other. And I have this new equation of motion for beta 2,1. Okay? And then I have the other equation of motion that I need to solve, which is this one over here. And this term can be replaced by, and let me do a new definition and define omega, capital omega, to be equal to mu d E naught over 2h bar. Okay, if I define capital omega to be that, and then if I define this to be just the imaginary part, this will become the imaginary part of beta 2. If you have beta 2, 1, if you subtract its complex conjugate, you get 2 times the imaginary part, right? You get I 2 times the imaginary part. Am I right? I guess so, yeah. 2 times the imaginary part of that. So that can be replaced with that equation. No, it should be here. I'm sorry, it should be here. It should be I 2 times the imaginary part of beta 2. Okay, not here. I'm going to make that simplification over there. Okay. So I have this equation of motion, this approximated equation of motion, together with this equation of motion. I need to solve them. Okay? I need to solve them. So in steady state, if you assume that the laser light is shining on this, then delta rho will reach a steady state. Delta rho is the population difference between the excited state and the non-excited state, or the ground state, okay? Delta rho will reach a steady state, and if that is the case, then I expect that the delta rho dt must be equal to 0. And if that is the case, I can set this equation to